I'm looking at the natural log of, or the integral of the natural log of x plus 1 times x to the negative 3 dx. So I'm going to walk up to this problem and say, is it algebra, trig, or a mixture of stuff? Well, it's a mixture problem because I've got a mixture of logs and algebra. I'm still quickly going to check for that u substitution. The derivative of natural log of x plus 1 would be 1 over x plus 1. I don't have that. And the derivative of x to the negative 3 isn't going to help me get rid of a natural log. So this must be integration by parts. Following our rule of late, logs come first in the word late, or that L comes first in the word late, which means that's going to become my u. For the integration by parts formula, I know that I need to find du. And then my other piece, my algebra, the x to the negative third dx, that whole thing becomes my dv. And to get the v that I need for the formula, I need to find the antiderivative of x to the negative 3 by adding 1 to the exponent and dividing by the new exponent. Adding 1 to the exponent, I'll be at x to the negative 2. So dividing by that would be at x to the negative 2 over negative 2. Now I'm going to put those together into my ultraviolet voodoo formula. Got ln of x plus 1 times x to the negative 2 over 2 minus the integral of 1 over x plus 1. And I realized there's probably a nicer way to write this, to put that x to the negative 2 into the denominator. So I will do that and have that as 1 over negative 2 x squared dx. So I cheated and I picked this problem because it started out as integration by parts. But now, in order to finish off the integral, we have another rational function. I'm going to take that 1 over negative 2 and pull that out in front of my integral. And I've got a rational function that's already factored for us. So I've got 1 over x plus 1 times x squared. The power on the top is obviously less than the power on the bottom. I don't have to worry about u substitution. I don't have to worry about doing long division first. I can go straight into thinking about integration by parts. I'm going to leave that 1/2 out in front and just focus on this piece. So 1 over x plus 1 times x squared. I can break this apart to say I've got x plus 1. And there are actually 2 ways to deal with the x squared. And I didn't talk about this yesterday, but we could think about x squared as being an irreducible quadratic. If we thought about x squared as an irreducible quadratic for a second, then that would mean what I would put on the top is bx plus c. And this works, but it's not usually the way we think about it. Because I have a single term in the denominator, I can actually break that up as 2 fractions to call that bx over x squared plus c over x squared. And on this term, one of those x's cancels out. This is actually why the general form, when we have some sort of repeated term to an exponent, this is kind of what's happening in the background. So we skip the step, we skip these 2 steps of writing it out, and we go straight to saying, because I have the x squared and it's repeated, I know that I need all of the powers of x that are 2 or less. And then each of these I treat as being a linear term, just the x, raised to some sort of repeated power. So both of these would just get a constant on top. If I multiply everything through by my common denominator, and that common denominator was x plus 1 times x squared. On the left-hand side, I get 1. And when I distribute that out on the right-hand side, a will need to be multiplied by x squared. B will only need to be multiplied by x plus 1. And C, one of those 2 x's will cancel out, but I'll still be left with an x and an x plus 1. This leaves me with 2 nice numbers to plug in. If I start by plugging in 0, I'll have a times 0, and here at the back I'll have c times 0. So that b term is the only one that's going to remain, and when I plug in 0 for x, I'll just get b. When I plug in -1, I'll have 1 is equal to a times -1 squared. When I plug in -1 here, I get 0, and when I plug in -1 here, I get 0. So it looks like a is also equal to 1. For our last value to plug in, we can choose anything we want. Just make sure it's something easy for you to do the math with. I'm going to choose +1. So if I plug in +1, and I keep in mind that I already know the values of a and b, this is going to look like 1 times 1 squared. B is 1, and 1 plus 1 is 2. And then at the back, I'll have c times 1 times 1 plus 1, or 2. Rearranging that, that's a 3, but when I subtract it over, I'll have -2 is equal to 2c. And if -2 is equal to 2c, c should be -1. We can go back to our integral at this point. And I think I'm going to have to erase this step. But I do want to make sure that I preserve that a was 1, b was 1, and c was -1. So we've got natural log of x plus 1 times, I lost a negative on that, -1 over 2x squared plus 1/2, and then we're going to have 3 separate integrals here. So the integral of 1 over x plus 1 plus the integral of 1 over x squared minus the integral of 1 over x dx. We're almost done. Here's our straightforward natural log. So ln, absolute value of x plus 1. This one, remember, it tricks a lot of students, especially on a quiz or any time that you're moving quickly, but 1 over x squared is not a natural log. because I could rewrite this as x to the -2 power. So when we add 1 to that exponent, we get x to the -1. This is going to become -1 over x. Here, this is our straightforward log, so I'd have absolute value of x plus a constant. So there are definitely times when we're going to have to use more than one technique for integrating. Maybe we're going